And we are solving because that's the directions. X is our variable. And we're only solving, notice that after the equation it says 0 degrees less than or equal to x less than 360. So our final answer are going to be values of x. They represent angles, to see how x is between 0 and 360. And I'm only looking one time around the unit circle to see where these things occur. Okay. Is that all right with everybody? Kind of the general idea. So then I have to actually solve this equation. So this is super complicated. There's a sine being squared, a cosine of double angle minus cosine of x is supposed to turn out to be 0. That would be really hard for me to guess and check different angles where those relationships would turn out to be 0 when there's so many things going on. So what I'd like to do is simplify that. To simplify it, I'd like to get the least amount of trig functions involved. If you give me something that's all about the sine, I am more likely to know where that happens on the unit circle than if the equation has sines and cosines and anything else in it, okay? So I want to kind of narrow it down to one trig function and find ways that will help me do that. So when I look at this, there is one thing up there. There's 3 terms on the left side. One of those terms I have no replacement for. I have nothing that I can substitute in for it. Which term am I talking about? So sine squared x, cosine 2x, or cosine x. Which one of those do I not have any identity that can allow me to simply substitute that for something else pretty quickly? Michelle? Cosine x. Okay. So that would be a hint to me that I'm probably going to want to try and rewrite everything else as cosine x's, because cosine x is the thing that's up there that I don't have anything to replace it with. Does that make sense to everybody? Okay. So then I want to ask myself, what do I have that can replace sine squared x? What do I have that can replace cosine of 2x? And can I write them in a way that they are just using cosine of x? And cosine of x is different than cosine of 2x, okay? Lauren? Okay, so the first thing I can do is the sine squared can become 1 minus cosine squared. So I have now taken out this extra trig function of sine squared, and I've made it all about something that has to do with cosines of x's. Okay. What about cosine of 2x? What can that be replaced with that's only about cosine of x? Savannah? Good. And then I have this. So actually, I'm going to treat this a lot like I would treat a quadratic. So I know you guys see up there, there's constants, right? The number's 1. There's cosine squareds, and there's cosines. That is a lot like having x squared, x's, and constants in some equation. And I like that it's set equal to 0 because if it is like a quadratic, if it is like I have something that's squared, something that's to the first power, and then a constant, quadratics were factoring if they were set equal to the approach that I'm going to take here. So I'm going to gather up all the like terms. So this x can be added with this negative squared x, and they'll just make 1 cosine squared x. Okay. Then I have this cosine x. And then the positive 1 plus the negative 1 will be 0. So here's what I have now. Again, remember, if something is factorable that is set equal to 0, that's a huge tool for you, because if you can break it up into parts that are multiplying each other and have it set equal to 0, you can know that either factor 1 could be equal to 0 to make that true, or factor 2 could be equal to 0 to make that true. That's called the zero product property, and you've known it since Algebra 1, but maybe not by its name. But it's an extremely powerful tool for us. So even though these aren't just simple x squareds and x's and they have cosines in them, there is a way for us to factor this. How could we factor this? Lauren? Good. We could take out the greatest common factor. They each have a factor of cosine of x. In the first term, that leaves one other factor of cosine of x. And in the second term, we would just have 1. So this is helping me because I have something multiplying something else to make the answer equal to 0. And that allows me to set up 2 smaller equations. Either the first factor has to equal 0, or the second factor has to equal 0. Okay? Okay. Now, this is much easier to solve because I can find angles between 0 and 360 where I know the cosine is equal to 0. And I can find angles between 0 and 360 where this is true. I'm going to simplify it just a little bit. Add 1 to both sides, and I have the cosine of x is equal to 1. So basically, the x's that are going to solve this equation are going to be the angles, I know it's an angle from the directions, between 0 and 360 that make this true or that make this true. Okay? So in my mind, the place I go is to the unit circle, and I think about 0 to 360 degrees. Okay? And let's think about this one first. Okay? Which angle or angles from 0 all the way to 360 have a cosine that would be equal to 0? Kenny. Okay, so 90 and 270. All right. And then what about this one? What angle from 0 to 360 has a cosine equal to 1? Savannah? Okay, so at 0 and at 360, and then look real careful at the inequality. Which one are we going to include? 0, because x, it doesn't include 360 exactly. So we're only going to list the 0. Not because 360 is not an answer to this question, but because it's not within the range that they wanted us to solve for x. Okay? So my answer here would be that x is equal to 0, 90, 270. All of those values of x, if you plug them back into that equation, would make the statement true. And if you're in doubt and you have extra time, plug them in and check. Take 0, plug it into the original equation, and simplify the left side and make sure you actually get 0. Take 90, plug it in, do the same. Take 270, plug it in, do the same. Okay? All right, are we okay with this? And so we're going to use a lot of these algebraic things and then our identities to substitute. So we're going to use this process a lot. Substitute stuff out to make it look like something I've already seen in algebra. I know it has the word cosine or whatever, but make it look like a quadratic. Make it look like linear, whatever. That then allows you to get through a solving process. Okay? All right, we're going to come back and let you guys do the try these later because I just want to make sure we have a shorter period today, but we have more practice time over the next 2 days that we get through all of the, like, we do together examples, and then over the next 2 days, you guys will have a lot of time to work together. Okay? All right. So this equation is simple to solve, but the parameters make it a little bit different when we're answering it. So we have to find out when cosine of theta plus 1 would equal 0, but for all the values of theta in radians. Okay? So not just for one trip around the unit circle, but for everything. Okay? So first, solve the equation. So I would subtract 1 from both sides, so that I'd have cosine of theta equals -1. No substitution here because it has nothing squared or anything like that. It's just a simple kind of linear type of equation. And then I want to think to myself, so even though this says find all the answers, let's think one time around the unit circle first. Okay? So if you just went one time around the unit circle, what angle would make this equation true, where the cosine's equal to -1? Brooke? Good, at 180. Okay? And we'll call it pi because they want the answer in radians. So pi is the only answer for one entire trip around the unit circle. Is that good with everybody? Okay. So what are the other answers going to be? Adam? Okay, good. So like this kind of like multiples of 180 or things that are coterminal with this spot, right? Okay. So this actually is very similar to how you guys wrote your asymptotes for the tangent, okay? Basically, this would become a list. It could be pi. It could be -pi, okay? Could it be 2 pi? No. But it could be 3 pi, 5 pi, and it would go on forever. And same with the negatives, and it would go on forever, right? So our answers is this infinite list of things. Just like we did with tangents, cotangents, secants, and cosecants on your graphing when you had to write this infinite list of places that you couldn't include in your domain, we wrote it as an equation, okay? So that's what we're going to do. You're going to tell me what theta can equal, okay? So it's going to be helpful for you to list the first solution, just like we used to list the first asymptote that we hit on the graph, right? So theta equals pi And then what do we do to end up back here over and over and over again? Ashley?
Pi plus 2 pi times squared, where k is an integer.
Good. All right, so how do we come up with this? If you wanted to land back at this spot after you've gone here, you have to travel completely around the circle. Are you guys good with that? Okay. Completely around the circle measured in radians is 2 pi. Okay. But could they go 5 times around the circle if they wanted and then stop and still be at the same place if we started at pi? Yes. So basically I'm telling them start at pi, go around the whole circle as many times as you want. But you can't go halfway around the circle or a quarter away. You got to go a whole time around the circle. That's why we say k has to be an integer. Okay. Any questions about this? So this is why we spent the time when we were doing asymptotes learning how to write this properly, because it comes in play here too, and then you'll use it later on in later years also. So this is our answer for all the values of theta that make it true. So if you think back to our trig unit when we did inverses, you guys are really doing inverse functions, right? To solve this, you're really doing this calculation, right? But previously when you were doing that calculation, we limited it, and the calculator limits it, right? So when you're doing a calculation with those things, we all get the same angle back. So when it says something like for all values of theta, then you no longer work in that strict parameter, and you list every possible solution. Okay? All right, there's lots of try these, like I said, but we're going to get through just the main one. Okay, so again, we're solving for all values. Okay? So once we get something that we think we can figure out which numbers solve it, we'll look one time around the unit circle, and then we'll translate that and explain what that means for all values. Okay? But again, like the first one, I look at this, I seen sine squared, a 1, a cosine squared. So a good strategy for me to use would be to make everything in terms of the same trig function so that it's easier for me to solve. So any idea of a substitution that you guys want to do? Good? Okay, so sine squared x minus 1. So 1 minus sine squared x is actually the cosine squared x one. Yeah, so it's like reverse, so it doesn't quite work. But we can take out the sine squared part and just call it 1 minus cosine squared, and then still have the minus 1, and then have the cosine squared. And if you chose to take the cosine squared out and replace it with 1 minus sine squared, that would work too. Okay? You should get the same answers. So here, on the left side, the 1 and the negative 1 add up to 0. Okay? So then I have negative cosine squared x equals cosine squared x. And then I'm going to go ahead and bring all of the cosine x's to one term. It's just like doing a quadratic, right? I'm almost treating these like they're x squareds. I would want to get them all on the same side before I decide if I can factor, separate them some other way, whatever it is. So I'm going to go ahead and add cosine squared x to both sides. So that makes this side 0, which is good for me. And this side 2 cosine squared x. So what should I do at this point in order to solve this equation? Good? Okay, so I should divide by 2. Good. So I get 0 equals cosine squared x. All right. What else? Okay. Yeah, we can square root both sides. Again, we're solving an equation now, right? So this is cosine x. Now, if this was like 1, it would leave us with a plus or minus 1. But given that it's 0, it's just still valued at 0. So now we have something a lot more understandable than the original equation that was up there. What that's asking us to do is the same thing as what this is asking us to do. So the value of x that makes this true is any angle x that has a cosine equal to 0. So again, even though it's for all of them, let's think one time first around the unit circle. So what are the positions one time around the unit circle where cosine of the angle would be equal to 0? Brooke? So 90 would be it. That's correct. What else? Anything else? Kenny? 270. Okay? Now, here's where it gets a little bit tricky. If these have no relationship, then your answer is like two separate equations you have to write, like 90 plus 360k, like where k can be any integer, and 270 plus 360k. However, 90 and 270 have a simple relationship, okay? And what I mean by that is, instead of saying 90 and then telling the person they have to go 360 degrees as many times as they want to land there, and then 270 and the same thing, is there a relationship between these two that you could say 90 plus some different amount besides 360, and then you don't even have to list the 270 separate? Or? Yes, you can. Okay, this one asks for degrees, so I'm actually going to do it simpler and do it in degrees. But, so x would be equal to 90. And so notice she said plus pi k instead of 2 pi k, meaning halfway around the circle as many times as you want, as long as you go a complete 180 degrees. Because if I'm on 90 and I go any amount of 180 degrees, I'm either going to end up here or here. And even if you go in the other way, right? So they would not list the two answers separately and say go around the entire circle. They would condense it into this one expression. Okay? Is this okay with everybody? Any questions about how we got this? So sometimes this works nicely and sometimes it doesn't. For example, if I have an angle, if one of my answers is here and one of my answers is here, and let's say that these are 90 degrees apart or something. This way from here to here is only 90. But if I go this way from this one to this one, is like 270 degrees or something, right? So I could not write one nice equation for both these angles, and I'd have to write two. These ones had the same distance between them in each direction, so that's why they could be condensed down to one pattern that you could follow to hit both of them.
How would, if you were to write two separate equations, how would you just go like one?
Yeah, you'd write like x equals this and or this other one too. Okay? All right. Okay, so this one, we don't have to write it for all, just between 0 pi and 2 pi. Okay, so 0 and 2 pi. And then we look at the left side. Do you think that I want to substitute anything on the left side, or do you think it's ready for me to start thinking of a way to work through it and solve it? Does it have all the same trig functions for everything that has a trig function? And does each trig function have the same angle in it? Yeah, they're all thetas. One of them's not 2 theta or theta over 2, whatever. I can't really make this much simpler than it is right now. This is a nice, simple, I'm using that term loosely. I'm not saying the equation is simple. I mean, it's in its most simple form that I could get it in. Okay. So what am I going to do with this? Does anybody recognize some patterns here that remind us of something else that we may have used in the past? Lauren? Good. So it's like a quadratic. See how you have the sign that's being squared, and then the sign, and then the constant? This is a lot like having this. It's just that instead of having x there, you have sine theta. Okay, so if it helps you, rewrite it like this for a minute. And I'm going to try and factor it. So I know I need 2x and x, and then I need a 2 and a 1, but they got to make a 3. All right. So that would factor like this. Okay? That means my equation over here that has sine thetas in it instead of x's factors like this. 2 sine theta plus 1 sine theta minus 2 equals 0. So again, if you're looking like, oh, I'm not going to know to factor, you have to look for some patterns that tell you to factor. This looks just like a quadratic, but it doesn't have x's. It has sines of theta. So when you see everything's been changed to one type of trig function, but you have some of it being squared, some of it's just to the first power, and then a constant, anything, whether it's trig, logs, whatever, anything that's fitting in that exponential type of pattern should remind you of quadratics, and you can use any of those things to solve it. Okay? So now that I have two factors set equal to 0, remember that allows me to say, okay, this one can equal 0, or this one can equal 0. Okay. This one over here, the sine theta minus 2 equals 0, if I go to solve that, I get this equation that says sine of theta equals 2. When does sine of theta equal 2? Never. Okay, so that I'm not going to get any solution from that. Okay? That doesn't mean there's no solution to this problem. It means that that definitely is not the thing that's making the 0 when they multiply. It's got to come from this one over here. Okay? So here, if I subtract 1 and then divide by 2, I have sine theta equals negative 1/2. Now that does happen, okay, and I need to figure out where. So visualize your unit circle. Where are the angles that sine of theta is equal to negative 1/2? Savannah? So 240, and where else? And 330. Good. Okay. So at our 30s, where the y coordinate is negative 1/2, we're looking there and there. So actually, this one should be 210, right? The 330 is right, yeah. So at 210 and at 330. And theirs are in radians, so we're going to answer it in radians. Okay, so remember, 30s are what in radians? Pi over 6. So if I know that this is pi, meaning it's 6 pi over 6, the one right after it would be 7 pi over 6. And if I know that the whole way around the circle would be 2 pi or 12 pi over 6, the one right before it would be 11 pi over 6. Okay. Since it only asks between 0 and 2 pi, I only have to list those two. I don't have to try and write them in a format where you could be any coterminal angle. It's all right? Okay. Is the solving now coming together from before? Okay, some different ways to do it. All right, so last one that we're going to look at. It looks like one of the simpler problems, but to me it's actually like the hardest problem on here. That's why it's example 5, not example 1. Why is this problem difficult? It looks so much like the last one we did looked hard, right? Look at all this stuff in there. Right? That looks crazy. This one looks so much simpler than that. But to me, it is more difficult to solve. Lauren? Good. There's no identity right now that I can swap out the sine for the cosine or the cosine for the sine. Why not? Why can't I just swap out the sine or the cosine here? Brooke? They're not squared. Good. So there's kind of two ways to do this. Some of you can do this intuitively, okay? And what I mean by that is you have good enough number sense and you're comfortable enough with the unit circle that you will literally just think in your head and figure out when the sine is equal to 1 plus the cosine at certain angles, okay? Jason's telling you right now because he's doing it intuitively, okay? For the rest of us, or if you change the numbers a little bit, not so intuitive, okay? But we're solving equations now. We're not proving identities. And your guys' issue with this is that I didn't have anything that was squared. What could I do then? I could square both sides if I wanted to, okay? Because I'm solving now. I'm not proving an identity. So if I want to, I can square both sides, okay? I have to be a little careful because sometimes squaring both sides makes extra answers in a problem. Problems that work when it's squared but don't actually work. So I just have to check at the end, okay? So if I square both sides, meaning I take this and I square it, and I take this and I square it, beware of the right side, right? It's not just 1 plus cosine squared. It's 1 plus 2 cosine x plus cosine squared x. Okay. So now that you squared and you have some stuff that's squared, what is the substitution that you would choose to make in order to make this all about one type of trig function and possibly factorable or solvable? Kenny? Good. Okay. So the reason I would do that is because this cosine right here can't be changed, right? So it's like I want to change everything into one of those when I see that. Right, and then I'm going to get everything on one side, so I'm going to go ahead and subtract 1 and add cosine squared x. And then do that same thing on the other side. So I'm going to get 0 equals 2 cosine x plus 2 cosine squared x. And now, again, it should remind you a bit of a quadratic, and you would try to factor that. The terms have a common factor of cosine and 2, so we can actually factor out a 2 cosine x, and that would leave 1 plus cosine x. And so then we'll split that into these two equations. And so basically our solutions will come from when cosine x is equal to 0 or cosine x is equal to negative 1. Okay. So where on the unit circle does the cosine of the angle turn out to be 0? Which angles? And they're in degrees, so we can just work in degrees. One time around, from 0 to 360. Where is the cosine equal to 0? 90, 70. And where is the cosine equal to negative 1? 180. So we're thinking 90, 180, 270. Now, because I squared both sides, I would just double check each of these before I list them as my final answer for x. So when I say double check, I mean I would check in the original equation. If I plug in 90, the sine of 90 is 1. The cosine of 90 is 0, and 1 plus 0 is 1, and those two things are equal. Okay? So 90 works. Good. When I plug in 180, the sine of 180 is 0. The cosine of 180 is negative 1. 1 plus negative 1 is 0, and those work. When I plug in 270, the sine of 270 is negative 1. Cosine of 270 is 0, and 1 plus 0 is positive 1. So that one is extraneous. And again, why does that happen? It happened because you squared both sides. For example, if I gave you guys a very simple equation, x is equal to 4. Okay, it's technically already solved. But look what happens. If you squared both sides, this would say x squared is equal to 16. And then if you solve that by taking the square roots, you would say that x could equal plus or minus 4. But what was the original statement? 4. When you square things, they lose some of their, you don't know if things were positive and negative, so then when you solve for them, you include the positive and the negative. And so sometimes that makes an extra solution that's not actually true in the original scenario. So we always have to check that. So it's good that we check, so 270 is excluded, and then these are the two solutions that I would come up with. Okay? Are we good with the idea of solving? Yeah?